Hello students, today we are going to discuss mathematical reasoning from class 11 maths. It is a new and interesting topic which would be helpful in further studies. So watch the video till the end. You must have studied sentences in English. In mathematics, a statement is a declarative sentence that is either true or false. A statement is a sentence which is either true or false but not both at the same time. For example, if I say every square is a rectangle, it is a statement. The sky is red. That is also a statement because it can either be true or false. Now, a sentence will not be a statement if it is an exclamation, it is an order or request, it is a question, it involves variable time such that today, tomorrow, yesterday, because you cannot be sure of its truth value. If it involves variable places such that here, there, everywhere, then also it will not be a statement. If it involves pronouns such that she, he, they, it is not clear. So in that case also it will not be a statement. Let us see some examples. The following sentences are not statements. Let us see why. Open your books. It is a command. It is not a statement. Y plus 9 is equal to 7. Now see over here. Y plus 9 is equal to 7 means basically y is minus 2. But nothing is said about y. Whether y is a natural number, it is an integer. So suppose if y is a natural number, then it is not possible because minus 2 is not a natural number. So nothing is specified regarding why it can be true or false, so you cannot say it is a statement. How are you is a question. Today is Monday, so today comes, so it will not be a statement. He is a good boy. He, so it is not a statement. Mathematics is difficult. Now since it is a subjective type of thing, so we cannot say it is a statement. The square of a number is an even number. Here also we do not know which type of number it is, integer, natural number, anything. Some definitions. A statement is called simple if it cannot be broken down into two or more statements. For example, 2 is an even number. A square has all its sides equal. These statements are simple statements. A compound statement is the one which is made up of two or more simple statements. For example, 11 is both an odd and prime number. This can be broken down as 11 is an odd number, 11 is a prime number. So, it is a compound statement. The simple statements which constitute a compound statements are called component statements. For example, find the component statements of the following compound statements. The number 100 is divisible by 3, 11 and 5. So which are the three component statements? The number 100 is divisible by 3, the number 100 is divisible by 11, the number 100 is divisible by 5. Similarly, 7 is a rational number or an irrational number. So 7 is a rational number, 7 is an irrational number. These are the component statements. Two lines in a plane either intersect at one point or they are parallel. What would be the component statements? Two lines in a plane intersect at one point. Two lines in a plane are parallel. Next, the words which combine or change simple statements to form new statements or compound statements are called connectives. The first connective is conjunction. What does that mean? If two simple statements P and Q are connected by the word and, then the resulting compound statement, which will be P and Q. Remember, P and Q are the notations for the statements. So P and Q is a compound statement and it is called conjunction of P and Q, and it is written in this form, P and Q. For example, translate the following statement into symbolic form. Jack and Jill went up the hill. Let P be the statement Jack went up the hill. Let Q be the statement Jill went up the hill. So, our given statement Jack and Jill went up the hill is in the form of P and Q. The connective is and. Now, regarding the truth value of the conjunction P and Q, the statement P and Q has the truth value true, which I denote by T, whenever both P and Q are true. And the statement P and Q has a truth value false whenever either P or Q both have the truth value false. Now remember, the table given below is called a truth table. It will be useful to you for in further studies also, in further standards. So it is very easy to remember if you remember in the form of this type of table. Like, suppose you have two statements P and Q. What are the possible values, truth values for P and Q? P is true, Q is true, P is true, Q is false. P is false, Q is true, and P is false and Q is also false. Now in each of the case, what will be the truth value for P and Q? When both P and Q are true, P and Q, this compound statement will be true. If say P is true, Q is false. Since one of them is also false, the P and Q compound statement will be false. So, what do we mean by this? P and Q, this compound statement is true only if both P and Q are true. Otherwise, in all other cases, it is false. The next logical connective is called disjunction. If two simple statements P and Q are connected by the word or, then the resulting compound statement P or Q is called disjunction of P and Q, and it is written as P or Q. For example, statement P is the sun shines, statement Q is it rains. The disjunction of P and Q is P or Q statement, which is the sun shines or it rains. The truth values for disjunction. The statement P or Q has the truth value false whenever both P and Q have the truth value false. The statement P or Q has truth value true whenever either P or Q or both have the truth value true. Now, if you remember this table, it will be very easy. So, what do we have for P or Q? P or Q is false only in one case when both P and Q are false. In all other three cases, P or Q has the truth value true. The negation of a statement. An assertion that a statement fails or denial of a statement is actually called negation of the statement. The negation of a statement is generally formed by introducing the word not at some proper place in the statement or by prefixing the statement with it is not the case that or it is false that. Negation of statement P is written in this way, negation of P, correct? Now, for example, if I want to write the negation of the statement P, which is New Delhi is a city, it can be written in following ways. Negation of P can be written as New Delhi is not a city. It is not the case that New Delhi is a city. It is false that New Delhi is a city. All these three are the negation of the given statement. The truth table for negation is very simple. When P is true, negation of P is false. When P is false, negation of P is true. We saw the three basic connectives. Now, this is an important thing. If P and Q are any two statements and the compound statement, if P then Q is called the conditional statement or an implication, and it is written in this form. You can either write P arrow Q or P if P then Q. When I am writing if P then Q, P is called the hypothesis or the antecedent. Q is called the conclusion or the consequent. The conditional statement if P then Q can be expressed in several different ways. Remember, this is important. If P then Q, this is the first way how you understand it. It can also be understood as Q if P. Third way is P only if Q. Fourth way, P is sufficient condition for Q. And fifth way is Q is necessary for P. We will see examples for this, so it will be clear that what is if P then Q. Now, what will be the truth values for the conditional? Remember, if P then Q will be false in only one case, when P is true and Q is false. And it is very well understood that you are having a statement if P then Q. When will that be false? Only in the case when your P is true but your Q is false. In all other cases, if P then Q will have the truth value true. Some points to remember. The negation of P and Q will always be negation of P or negation of Q. Actually, this is like the De Morgan's laws which we have studied, and you can verify this using the truth table which we are having. But for time being, you can remember that negation of P and Q is negation of P or negation of Q. Similarly, negation of P or Q is negation of P and negation of Q. And will change to or will change to and. Negation of P is the given statement P itself. Now see, there are three things. You know that if P then Q is called the conditional. You can have converse, which is if Q then P. This is called the converse of the conditional. You have the inverse of the conditional, that is negation. If negation of P, then negation of Q. And you have contrapositive, which is if negation of Q, then negation of P. So these three things are there. This table very well shows it. So for any conditional if P then Q, you can form the converse, inverse or its contrapositive also. Like you have the conditional, you also have the biconditional. If two statements P and Q are connected by the connective if and only if, which is very much used in maths, then the resulting compound statement P if and only if Q is called the biconditional of P and Q, and it is denoted in this form, if P if and only if Q. What will be the truth values for the biconditional? When both P and Q are true, P if and only if Q will be true. If P is true, Q is false, then it will be false. If P is false, Q is true, then also it will be false. But if both P and Q are false, then P if and only if Q will be true. So now next thing is quantifiers. For any statements you have quantifiers, which are the phrases like there exist, for every. You have come across these phrases in maths. For example, if I have the statement P, which is for every prime number x, x is an irrational number. I can also have a statement of this kind, there exists a triangle whose all sides are equal. So in these cases, there exist for every are called the quantifiers. Remember, we will discuss examples on each of these things, so it will be very clear. We will start with the first example. Which of the following statements are compound statements? 2 is both an even number and a prime number. This is a compound statement. Which are the component statements? 2 is an even number, 2 is a prime number. 9 is neither an even number nor a prime number. Its component statements, it is compound, and the component statements are 9 is an even number, 9 is a prime number. Then you have the connectives with it. Ram and Rahim are friends. This is not a compound statement because you cannot break down into component statements. Next example. Are the following pairs of statements negations of each other? First one, the number x is a rational number. The number x is an irrational number. Both are negations. Why? The second statement is the number x is an irrational number, means it is not a rational number. So the pair of statements are negations of each other. Second case, the number x is not a rational number. The number x is not an irrational number. Now see, the number x is not a rational number. Its simple negation will be the number x is a rational number. But the second statement also means the same. The number x is not an irrational number means the number x is a rational number. So basically both the statements in the pair are negations of each other. Third case, x plus y is equal to y plus x is true for every real number x and y. Second statement in the pair is there exist real numbers x and y for which x plus y is equal to y plus x. Now these are not negations of each other. Why? The first statement says x plus y is equal to y plus x for every real number x and y. So its negation is x plus y will be not equal to y plus x for any real numbers x, y. So the second statement here is there exist real numbers x and y for which x plus y is equal to y plus x. Obviously both are not negations of each other. The negation of the statement 72 is divisible by 2 and 3 will be which out of the following? Now see, the statement is 72 is divisible by 2 and 3, means the given statement says that 72 is divisible by 2 and 72 is divisible by 3. So the negation of this statement would be 72 is not divisible by 2 or 72 is not divisible by 3. Remember, we had studied the laws like the De Morgan's law. The negation of a statement of the type negation of P and Q is negation of P or negation of Q. So the negation would be 72 is not divisible by 2 or 72 is not divisible by 3. Similarly, the negation of the statement the product of 3 and 4 is 9. So what does this say? The product of 3 and 4 is 9. The negation would be it is false that the product of 3 and 4 is 9, because obviously nothing of the type is given the product is 12 or anything of that kind. So the simple negation is it is false that the product of 3 and 4 is 9. Example 3. Write the component statements of the following compound statements and check whether the compound statement is true or false. 57 is divisible by 2 or 3. The component statements are 57 is divisible by 2, 57 is divisible by 3. Now remember, the given statement is having the connective or, so it is of the kind P or Q. I have given the table for P and Q. So when P and, so over here 57 is divisible by 2. Is it true or false? It is false. 57 is divisible by 3. This statement is true. So when P is false and Q is true, then the given statement is true. P or Q is true. Second case, 24 is a multiple of 4 and 6. Component statements are 24 is a multiple of 4, 24 is a multiple of 6. Both the component statements are true. So P and Q will be true when both P and Q, both of them are true, and in this case both are true, so the compound statement is also true. Example 4. Remember, this is a new and different type of topic, mathematical reasoning, so try to understand each and every example. Fourth example, write each of the following statements in the form if then, or it is also called conditional. First one, you get a job implies that your credentials are good. So in the form of if then you can write, if you get a job then your credentials are good. Second, the banana trees will bloom if it stays warm for a month. If the banana trees stay warm for a month, then the trees will bloom. Remember here if is with the component statement banana trees stay warm for a month. So the given statement if written in the form of if then is if the banana trees stay warm for a month then the trees will bloom. Third case, the square of a prime number is not prime. If the square of a prime number is taken then it is not prime. Right? So first of all, if you take the square then it can be either prime or not prime. So it is of the form if the square of a prime number is taken then it is not prime. To get A plus in the class it is necessary that you do the exercises in the book. Remember this is given in the form of necessary condition. So if you want to score A plus in the class then you do all the exercises in the book. Once again refer to the if P then Q definition which we had seen, in which 5 ways it can be written. So it will be clear. Fifth one, a sufficient condition for Tara to visit New Delhi is that she goes to the Rashtrapati Bhavan. Now since sufficient is for Tara to visit New Delhi, it will be forming Q. So if Tara goes to Rashtrapati Bhavan, then she visits New Delhi. So whenever sufficient condition for Tara to visit New Delhi is given, it is given in this form, sufficient condition, then it will be if Tara goes to Rashtrapati Bhavan, then she visits New Delhi. Example 5. Given statements in A and B, identify the statements given below as contrapositive or converse of each other. Means you have to say whether they are contrapositive or they are converse. So I have given the table on one side, so it will be very clear. If you live in Delhi, then you have winter clothes. If you do not have winter clothes, then you do not live in Delhi. Which type of statement would be this? Original statement is if you live in Delhi, then you have winter clothes. So P is you live in Delhi, Q is you have winter clothes. Correct? So it is of the kind if P then Q. Now here the second statement which is given is if you do not have winter clothes. That means it is negation of Q. You do not live in Delhi. So it is if negation of Q, then negation of P. If negation of Q, then negation of P is contrapositive statement. You can see in the table. Second case is given, if you have winter clothes, then you live in Delhi. That means it is of the kind if Q, then P. So if Q, then P is called the converse of if P, then Q. Correct? Second example, if a quadrilateral is a parallelogram, then its diagonals bisect each other. For this given statement, let P be quadrilateral is a parallelogram, Q be diagonals bisect each other. So it is of the kind if P then Q. First statement, related statement which is given is, if the diagonals of a quadrilateral do not bisect each other, then the quadrilateral is not a parallelogram. So it is of the kind if negation of Q, then negation of P. So what is it? It is the contrapositive of the given statement. Please remember and refer the table I have given over here. It will be clear. Second related statement is if the diagonals of a quadrilateral bisect each other, then it is a parallelogram. So here it is if Q then P. So if Q then P is nothing but the converse of the given statement. Example 6. Form the biconditional statement P if and only if Q where, first case, P is the unit digit of an integer is 0, Q is the integer is divisible by 5. Solution, the unit digit of an integer is 0 if and only if it is divisible by 5. Second example, P, a natural number n is odd, Q, natural number n is not divisible by 2. We want to write in the form of biconditional. So it is a natural number n is odd if and only if it is not divisible by 2. Third, P, a triangle is an equilateral triangle, Q, all three sides of a triangle are equal. A triangle is an equilateral triangle if and only if all its sides are equal. This will be the biconditional. Next example, identify the quantifiers and write the negation of the following statements. There exists a number which is equal to its square. The quantifier is there exists, correct? What will be the negation of the given statement? There exists a number which is equal to its square. There does not exist any number which is equal to its square. Basically, just remember one thing. When you have there exists and when you take the negation of it, there exists means there exists some number. And its negation will always be the opposite of it. That means for all numbers, this thing is not true. So, whenever the given statement is there exists a number which is equal to its square, negation will be there does not exist a number which is not equal to its square. That means there does not exist any number basically which is equal to its square. That will be the negation. Second case, now the quantifier is for all even integers x square is also even. So here the quantifier is for all, correct? So when the quantifier is for all, the negation will be there exists some. So there exists an even integer x such that x square is not even, correct? This will be the negation. Third case, again there exists a number which is a multiple of 6 and 9. So here the quantifier is there exists. What will be the negation? There does not exist any number. Basically it is any, but you can write in simple ways as there does not exist a number which is a multiple of both 6 and 9. Now see, while defining if-then type of conditional statement, we had seen we can write it in 5 different ways. So the next example says that rewrite the following statement in if-then form in 5 different ways. The given statement is, if a natural number is odd, its square is also odd. So the here conditional statement is if P then Q. Now by definition it can be written in the 5 ways given over here. Let us write in one by one each of the ways. First is a simple way, if P then Q. That means if a natural number is odd, then its square is also odd. This is the simplest way. Second one, Q if P. That means the square of a natural number is odd if the natural number is odd. Third case, P only if Q. A natural number is odd only if its square is also odd. Fourth and fifth case, these are a little bit difficult, try to understand. If P then Q, P is sufficient for Q. It can be written as P is sufficient for Q. That means for the square of a natural number to be odd, correct? That means for Q, it is sufficient that the number is odd. It is P is sufficient. That means it is sufficient that the number is odd. For the square of a natural number to be odd, it is sufficient that the number is odd. This is for sufficient. Q is necessary for P. So over here, for a natural number to be odd, it is necessary that its square is also odd. Q is necessary for P, correct? So for a natural number to be odd, it is necessary that the square is odd. Now we move to the next concept, which is checking the validity of the given statements. Here our truth tables will be helpful to us. Validity of a statement means checking when the statement is true and when it is not true. This depends on the connectives, quantifiers used and the implications. First thing is validity of the statement with AND. This is very simple. If we refer to the table for AND, it is very clear that P and Q is true. If I want to show that P and Q is true, I need to show that P is true and Q is true. Both are true. Validity of the statement with OR. To show that P or Q is true, you can show either P is true or Q is true. Correct? So this depends on the truth table which we have seen. Now this is important. How will you check the validity of the statement if then? Means the conditional type of statement. To show that the statement R, which is of the form if P then Q, I want to show that R is true, then we can use any of the following methods to show if P then Q is true. First is the direct method. Assume P is true and show that Q is true. Simple. Second is the contrapositive method. We have seen previously what is contrapositive. So by using this method, what we have to do is you assume that negation of Q is true and show that negation of P is true. So this will imply negation. If negation of Q, then negation of P. So this is same as if P then Q. Contradiction method. In this you have to assume that P is true and Q is false and then obtain a contradiction from our assumption. We know that if P is true, Q is false. This is not possible in the case if P then Q is true. So what we do is we take an assumption that P is true and Q is false, and from this assumption we obtain a contradiction. Fourth is by giving a counter example. Simple way to give a counter example. To prove that the given statement is false, we just give a counter example. For example, say our statement is if x is a prime number, then x is odd. So I want to show that I want to check the validity of this statement. Then the statement will be false. Why? Because 2 is a prime number and it is also an even number. So the given statement is false. Validity of the statement biconditional, if and only if. To show that P if and only if Q is true, we can do it in two ways. First step is show that if P is true, then Q is true, and second step is if Q is true, then P is true. Both the things you need to show. Example 9. Prove by the direct method that for an integer n cube minus n is always even. Take two cases, n is even and n is odd. Use the direct method. Once again I am repeating what is the direct method. Assume P is true and show Q is true. So what is our statement P? N is an integer. What is our statement Q? N cube minus n is even. Correct? So now first case is if n is even. Now if n is even, n cube minus n can be written as n into n square minus 1. And this will always be even. Why? Because n is even and anything you multiply by an even number, it will always be even. Correct? So in this case, it is proved. Second case, if n is odd. Suppose if n is odd, then take n is equal to say some 2x plus 1 for some integer x. Correct? So n will be odd. Now n cube minus n will be n into n square minus 1. For n you put 2x plus 1. Simplify this term, 2x plus 1 whole square minus 1 square, a square minus b square type of thing, a minus b into a plus b. So when this is simplified, you get 2x plus 1 into 2x plus 2. Now you can see anything multiplied by 2 will always be even. So what we have shown is if P is true, then Q is always true. This is by the direct method. Example 10. Using contrapositive method, prove that if n square is an even integer, then n is also an even integer. First, let me repeat what is contrapositive method. Assume negation of Q is true and show negation of P is true. Correct? If you can show this, it means that if P, then Q is true. So our statement P is n square is an even integer, Q, n is an even integer. Correct? So we assume that negation of Q is true. That means let n not be an even integer. What does this mean? Since n is not an even integer, n is an odd integer. N is an odd integer, so again write n as some 2x, n is equal to 2x plus 1 for some integer x. So now when we simplified n square, what do we get? 4x into bracket x plus 1 plus 1. This is how we can simplify. But since it is plus 1, 4x into x plus 1 is even and that plus 1 will always be odd. Correct? So we have shown that what we had assumed negation of Q is true, and what we have shown, negation of P is true. Correct? Because we have shown n square is odd, we have shown that negation of P is true. Hence, from this we can say if P, then Q is true. Example 11. Show that if x is a real number such that x cube plus 4x is 0, then x is 0 by the method of contradiction. First thing is I am repeating, contradiction method means you have to assume that P is true and Q is false, and from that assumption you will get a contradiction. So this will show ultimately that if P, then Q is true. Now over here our statement P will be x is a real number such that x cube plus 4x is 0. And what is statement Q? X is 0. So if I want to show if P, then Q is true, by this method what we do is we assume that P is true and Q is false. That means we are assuming that x is a real number so that x cube plus 4x is equal to 0. And we are also assuming that x is not equal to 0. Now x cube plus 4x is equal to 0. If I simplify it, it is x into x square plus 4 equal to 0. But we know that what does this mean? This means either x is 0 or x square plus 4 is 0. But x square plus 4 cannot be 0. So what is the possibility? X is equal to 0. So our assumption that q was false, that means x is not equal to 0, this assumption is not true. We are getting a contradiction to our assumption. Therefore, by the method of contradiction, we have shown that if x is a real number, then x cube plus 4x is 0, then x is 0. So this is the method of contradiction. You assume that p is true and q is false, and from that you get some contradiction. So this will ultimately show that if p, then q is true. Next example. By giving a counter example, show that the following statement is not true. If all angles of a triangle are equal, then the triangle is an obtuse angle triangle. As we saw previously, giving a counter example means you just give an example in which the case does not hold. So now we know that if all angles of a triangle are equal, then each angle is 60 degree. Why? Because the sum of all angles of a triangle is 180 degree. If all the angles are equal, then each angle will be 60 degree. 60 degree, each angle is 60 degree. That means there is no obtuse angle. That means it is not an obtuse angle triangle. So by giving a counter example, we have shown that the given statement is false. So basically you can adopt any of the ways to show that the given statement is true or false, to examine the validity of the given statement. See students, this is a interesting yet confusing chapter. In case of any query, please write in the comment section. We have seen mathematical reasoning of class 11, which is just an introduction. We will study it further. Please like and share the video and subscribe to the channel.